We are going to build a simulation or behavioral model for an op-amp. We are going to start from scratch and develop the behavioral model systematically, step by step. As we mentioned, this also applies to amplifiers in general and not just an op-amp. We have already introduced the ideal op-amp earlier in the course. This schematic of the op-amp should be quite familiar by now. It has been repeated quite a few times. And this was done so that the student can become familiar with it. We already pointed out that this circuit has a differential input. And we also showed that if one of the terminals of the op-amp is grounded, it becomes a single-ended input. The output is always referenced to ground and it is single-ended. The 5 characteristics of an ideal op-amp is also shown. As we shall see, these assumptions help with circuit analysis, but it should not be taken to the extent illustrated in the previous example. However, this is a fine line and we shall often refer to it and point out what the useful applications of these assumptions are. We start with the input side characteristics. The input current is 0, followed by the infinite input impedance, and the 0 input voltage between the two terminals. This is followed by the output side characteristics. The gain is infinite, and the output impedance is 0. The output voltage is equal to the gain multiplied by the difference between the input voltage terminals. Note that these characteristics are a bit contradictory. The output voltage is equal to the input voltage difference multiplied by the gain, but keep in mind that the assumption is that the gain is infinite, and the input voltage is 0. This shows the limitations of the application of these assumptions. We are going to use LTspice extensively to develop our behavioral model. Our model is a behavioral model, which means it simulates the behavior of an op-amp, rather than replicating the actual transistor circuit inside it. This approach is different than the exact component-level representation of an op-amp. We shall get to that later in this module. We implement the simulation model as an equivalent circuit using LTspice. We start with a rather simple equivalent circuit, and then add more complexity to fully model an op-amp. This leads us to the question, how do we simulate the ideal op-amp in LTspice? This is what the simulation model for the ideal op-amp looks like in LTspice. It is clear that there are several characteristics that are not the same as the ideal op-amp. This model has infinite bandwidth. This is taken from the data sheet of a real op-amp. As can be seen, the gain is between 73 decibels and 87 decibels. It is high, but not infinite. The LTspice model is supplied with a small 1 microvolt signal with a frequency of 10 kHz. This signal drives into an input impedance of 100 megaohm. This is the input resistance of the op-amp. But, unlike the ideal op-amp, it is high but not infinite. This means the input voltage is not 0 and the input current is also not 0. Both are extremely small values, but not 0. In this example, the input current is in the picoamp range. The amplification is implemented with a voltage-controlled voltage source, with a gain of 100,000, or 100 dB. This is shown in the schematic as E-gain. The gain is equal to 100,000, or 100 dB. The model has a 100 milliohm output resistance. The op-amp drives into a high-value load resistor, in this case it is 100 megaohms. This is a non-inverting amplifier. The negative input is grounded and is common with the output circuit. The positive terminal of the signal source is connected to the positive input of the model. The output is a single-ended output. In this slide we show what the input and output signals look like for the ideal op-amp in the previous slide. These signals were generated by LTspice. This is the input signal. The amplitude is 1 microvolt and the frequency is 10 kHz. The gain was set at 100,000 or 100 decibel. The output signal is 1 volt peak, which is 1 microvolt multiplied by a factor of 100,000. The input and output frequency are obviously the same. This is the end of this section. In the next section, we are going to investigate what the infinite bandwidth means.